classes. You have received an email, well, a message from VIP with the links to the videos. I promised the videos for Saturday, and then we will discuss them today, but we had a change of plan. Things essentially to give you a bit more, maybe a bit more time to have a look at the project before tomorrow's lab discussion. We decided to move those flip classes to Friday. So we published the two videos yesterday, and then we will discuss them on Friday. So today actually we will not, of course, have the discussion on the videos. So today we will finish the part on architectural styles, and we will have a look at architectural patterns, especially for the cloud world. And then we will move to today part of the arguments that were planned for Friday, and which are a couple of case studies concerning architectures. So on Friday we will instead we will discuss the videos, and we will focus on the more quantitative part of this architectural part. We will analyze some techniques. We will provide an overview to some techniques for quantitatively analyzing architectures in terms of availability, reliability, and these kind of figures. So this is the plan for today and for Friday. Tomorrow, one word about Friday. So the two videos, one of them is accompanied by the usual questionnaire, and again, we ask you to have a look at the video and then answer the questions in the questionnaire, which are essentially for, let me say, consolidating what you heard in the video. So we are not evaluating you on the questionnaire. We take the names, so we look at we see who is more or less who's answering. So please have a look at it anyway. The answers are quite easy. You should be able to. I mean, it takes 10 minutes to look at the videos, to look at the video, the part on the part with the questionnaire on design process, and then 5 more minutes to answer the questions. The other video, the one on design principles and design views, the video is itself a bit longer, it's some 20 minutes, and we will discuss that in class in a slightly different ways, in the sense that we are going to try out a different way of interacting. We are going to use a software called Mentimeter, where I will give you a couple of questions live, and you will be able to answer them actually using by logging on the website, or not logging, by clicking on the website and actually providing answers there. You can do that using your cell phone. You can do it using your computer. So this is what we are going to try out on. This is what we're going to try on Friday. Then tomorrow, project. So you saw, of course, so we published the project last week, and then on Friday we also actually published the assignment about the implementation. So you have a look at you are able to have a look at that. Of course, at the same time we opened up the registration for the implementation and testing part of the project. But that registration part closes like end of November, so you have plenty of time to still think about that. We published the implementation and testing assignment so that you can start having a look at whether your intention is to actually do the implementation and testing part. It might have helped some of you define the groups. There has been some dynamic groups creating, disaggregating, and then reforming. So maybe the implementation and testing part played a part on that. Someone who decided then not to do the implementation and so on. So essentially, right now, all the project assignments for the Track Me project has been published. Mandatory part, requirements and design, and also implementation and testing. We still have to publish the themes for the research topics, and I guess we will do that during the month of October, so fairly soon, I would say. We haven't set up a date yet, but probably we will need to do that, I would say, either next week or anyway before the 1st of November. So we are also going to publish them quite soon. So then tomorrow morning we will discuss the project. So please read the project so if you have questions tomorrow. So tomorrow we will analyze what you are supposed to do, what you are supposed to provide in terms of the project, and we have already selected a project from, I mentioned that the first class, we have selected a project from last year. We have anonymized it, so you don't see the names of the people. But in any case, I mean, it's not a bad project. So even if it were not anonymous, it's not a bad project. So we selected this project from last year, and the idea is that tomorrow, maybe not during the class, probably later, we will give you the project, and that project will be for you to criticize. So next week, next Wednesday, 24th of October, we will have another lab session. In that case, we will discuss the project that we are going to give you tomorrow or today, probably tomorrow. And the idea is to criticize it, to point out errors so that you don't take the same errors this year. And for that part, let me remind you that we are also going to publish a questionnaire that you're going to fill out by group. So each group, not individually in this case. So in this case, that questionnaire will have to be filled out by group. And actually, it's going to be part of your evaluation. It's going to be worth 1 point. It shouldn't be a difficult point to get, because essentially you have to look at that. It takes I would say the project for the requirements part is some 40 pages, but I mean it's not you can read it in I would say a couple of hours, I guess, and then it takes a bit to think about that and maybe point out possible weaknesses of the project. So it takes a few hours to work on that. Again, it's worth a point. Because we are going to ask you to fill out the questionnaire, and also then we are going to actually score that questionnaire, and that will be one of the available 16 points for the mandatory project. Again, it's probably not going to be a difficult point to get with just a bit of work. It's not like, oh, you didn't realize that there was this mistake, so I'm going to dock you half a point or even the full point. Of course, if you write nonsense, I'm going to dock you at least part of the point. But if you write meaningful things, reasonable things that could be fixed and so on, again, it shouldn't be difficult for you to get the point. But that part is going to be scored. So the questionnaire that we're going to give you concerning last year's project, that one is going to be scored. All right, so it took me some 10 minutes, a bit less than to explain the next few steps. Now, so today let's finish the part on architectural styles. So the idea is that so we started looking at a few styles last time. We started with the classic client-server, the classic client-server style. We also had a look at the so-called layered style used for operating systems, for example. And then the client-server style that's again very well known. Typically, so request-response mechanism. So a client sends a request to the server answers with a response. That's the general scheme. Then the client-server style actually can be instantiated in different flavors, in different tiers. In particular, the question is, so we have two sides, the client and the server. That is, let me say, a classic, I would say, two-tier architecture. So two tiers: the client tier and the server tier. But actually, as you will see in a second, we can also spread the logic around also to multiple tiers. Even when we have two tiers, so the client tier and the server tier, there is an architectural decision to be made, which is where to put most of the logic of the application. The idea is that, of course, the application has some logic, elaborate some data, imagine something that provides statistics, for example. So there's a logic there concerning, for example, the computation of statistics. The question is, where do you move the balance of the computation? Is it more on the client side, or is it more on the server side? If it's more on the client side, then we get to the approach called of the fat client. So the fat client contains a lot of logic. If you move most of the logic on the server side, then you have more of a so-called thin client, very lighter weight, and the logic is on the server side. Still, you can distribute the load of the computation quite, let me say, regularly. Let me say across the two tiers. So just to this picture show you, depending on, let me say, where the network is. So depending on, the network, if you want, is the barrier. So the network and with respect to the network, depending on where the logic is. So the gray part, the application part. That is the logic. So essentially, we have the logic, which is the gray part, and depending on where the logic is, we have more of a fat client or more of a thin client. In any case, whenever we have a client-server application, we typically have three elements. So the logic, the gray part, but also, so the client typically is the front end to the user, let me say. The user could be like a person, so it could be a graphical interface, it could be maybe even another interface. But typically on the client side, you have some sort of interface. So the green part, in this case, it's a graphical user interface. That is the interface on the client side. That is one element. Then the logic, the gray part, and then the data. So the data, that is the red part. Again, imagine an application that computes some, for example, statistics. The data. This is where what you calculate your statistics on. So depending on where the network is, we have more of a thin client or more of a fat client, and also we have different flavors for this client-server architecture. So essentially, if the logic is more on the server side, we said this is a thin client. If the logic is more on the client side, this is more of a fat client. But still, we have several flavors. So for example, in this case, everything is on the server side, even part of the interface. So in this case, essentially the idea is that the server computes everything, including what to show. And then on the client side, you only need to present what was determined by the server. So in this case, we talk about distributed presentation. This is a very thin client because it only displays stuff. It doesn't even compute how to arrange, for example, the graphics. So this is a very thin client. A slightly lesser thin client is the case of the remote presentation. In this case, the logic is entirely on the server side. So the logic is entirely here, also the data. However, the client side at least decides how to arrange the data, to arrange the information to show to the user. So this is more of a so-called remote presentation. And then imagine that we split a bit of the logic on the client side and a bit of the logic on the server side, so that the client becomes a bit fatter. So this is more of a distributed logic. So distributed logic, because there is some logic on the server side, but also some logic on each client. So each client has its own logic. So that's why we talk about distributed logic. And then we move all the whole logic on the client side. So in this case, on the server side, we only have the data. we only have the data. Client side has the interface and the logic. So in this case, it's a remote data access scheme. Remote data access because the only thing that is remote is the data. Everything is on the client side. This is a fact client. And then we have another possible approach where even some of the data is distributed. And in that case, the server side is very, very light. And we have some data, or we say it's lighter, and we have some data also on the client side. So in this case, we talk about the distributed database because part of the data is also on the client side. Just to give you an idea, again, last year we have presented you briefly the idea of last year's project, the Traveler Plus, the calendar, and so on. We are going to, of course, we will need it to understand the project to be criticized. But for example, last year, just to give you an idea, last year we saw during projects a few variations, a few possibilities. Some people last year, for example, decided to go more for let me say a remote presentation style where the logic is entirely on the server side, but someone actually chose to go towards more of a remote data access approach where the logic was entirely on the client and actually only the data was on the server. So even in your projects, you might actually end up using one of these styles. And which one is best for you? Well, it depends from a lot of factors, your requirements, maybe some performance considerations, and so on. As I said, so this is a two-tier architecture, client-side, server-side, but actually the server side can be spread out to more servers, actually. So we go to a so-called three-tier architecture. And by the way, typically these issues are also tackled in other classes, maybe also in a bit more depth. I think when you do information systems, there's also discussion about these things. But let's just provide an overview of these things, and you might probably see a bit more details in other classes. But in the three-tier architecture, this is another classic structure for information systems. The server part, so the logic and the data are also separated over different servers. So in this case we have a stronger coupling between logic and data. If we actually separate further logic from data, we get to a three-tier architecture where the network is not only between the client and the server, but also within the server, between, for example, the logic and the data. So this is a three-tier architecture. So this is an example possible architecture for a supermarket management application where you have the client that, for example, needs to query the system to get information, again, statistics about products, who buys more, and so on. Then there's a logic, there's the application logic that computes, for example, the information, which is the second tier, the gray tier, and this is a server. But then there are separate servers. So you see the red part, the data part, is itself distributed over different servers. So we have different servers, maybe one per company. So the Checo, Plasmon, or maybe customers, and so on. So we have separate data servers on the third tier. So first tier, second tier, third tier. So we have three different tiers. We separate the client side, the application logic, the business logic, the computations to be made, to be carried out, and so on, and also the data side, which is also distributed. And of course, once you move from 2 to 3, you can think of moving from 3 to 4 and then 5, and actually it's difficult to have a multi-tier application. Usually, in many cases, I would say it's a 3-tier 2-tier or 3-tier. But actually, you could also further decouple, maybe introduce a further layer between certain data servers. So, for example, maybe certain data needs a specific logic, which is also put on a separate server. So imagine that. By the way, customers. So this should be customers. I see it now, not customers. So maybe the part about the customers doesn't need a specific logic, so it can be, let me say, linked directly. But the part about managing data from the producers, from the providers of products, and so on, maybe that needs a specific logic that can be externalized on a separate server. So we move from 3 tiers to 4 tiers, and I don't know, possibly even more. Okay, so this is the classic client server architecture. A bit more, let me say, modern. Client server has been around for decades. The so-called event-based systems have also been around for a couple of decades, but definitely less popular, even though they are becoming more and more popular, more and more used in practice. So the idea of event-based systems is that in this case you do not have requests and responses. So remember, client server is a classic send a request, get a response. In an event-based system, the idea is that components, they react to, again, events, essentially. So someone produces events and someone consumes events. Now, who produces, essentially registers as a producer, who consumes registers as a consumer, but registers to whom? Registers to a so-called event dispatcher. So there's a, let me say, you can think of it as a bus, but it's not really a bus. It's essentially an intermediate component that takes events from the producers and distributes them to the consumer. But the decision on who receives the events is actually made by the receivers. So it's the receivers who register, who decide, well, from now on, I want to subscribe, I want to get this information. So what happens is that clients, for example, client C4 registers, so the arrow is for registration. So client C4 registers on the event dispatcher, and then client C1 maybe also register. So now clients C1 and C4, they are registered to receive the events, and then a producer, so for example C3, produces an event. So what the event dispatcher does is determine who subscribed to that type of event and distributes the event and distributes the event to the clients who registered. As you might have understood from what I just said, the registration is based on the type of event. So when you register to an event, you don't say any event. Well, you might even say any event, but that's let me say the most general type of event. So the idea is that typically clients, they register to receive a certain type of events. When producers produce events, they say, well, this is an event of a certain type, and then the event dispatcher matches the types of the incoming events with the registrations, and then spreads the notification to the various clients that registered. So, and this is not in this case, again, the dispatcher broadcasts the events to all registered components. So it's a broadcast mechanism, but based on the registrations of the made by the client. So this event-based architecture is also sometimes, well, I would say in many cases, called publish-subscribe architecture. So publish-subscribe, so the producers, they publish events, and the receivers, they subscribe to events and then receive them. So the publishing So the publishing corresponds to the generation of the events by the producers and the subscription, that's the so-called declaration of interest. So essentially, give me certain types of events. There are several frameworks for managing publish subscribe mechanisms. Typically, each one of them has its own primitives for example, for registering, for publishing, and so on and so forth. These types of event-based architecture are more and more popular because they actually they allow us to create a loosely coupled architecture. Loosely coupled in this sense. Clients, producers and consumers, they actually don't know one another. So when the producer produces events, it doesn't know who will receive them, because who receives them is entirely under the control of the subscriber. So the producer has no control on who receives the events. On the other side, the subscriber has no control on who publishes the events. The subscribers, they do not know the identity of the producers of the events, unless, for example, the event itself contains some information about the identity. But in principle, the subscribers, the receivers, they do not know who produces the event. So there's contrast this with the client-server architecture. The client-server architecture, the client invokes a specific server, and the server receives the invocation from the client. So essentially, they know one another. Well, the server might not really know the client, but the client in particular, it knows precisely to what server it is sending the request. Whereas in this case, the two sides are completely decoupled, so they don't know one another. This allows, for example, to add producers and consumers dynamically. And by the way, producers and consumers, they are not separate roles. I mean, the same component could be a producer of some events and a consumer of other events. So much like in the client-server architecture, where a client could also be a server and vice versa, in event-based architectures, some components could both produce events and also receive other events. In this architecture, it is easy, for example, to add new producers, add new consumers, even dynamically become producers and consumers. It happens, for example, that a component subscribes to some events for some time, then decides that certain events are not necessary any longer, so deregisters, de-unsubscribes, and then resubscribes to other events, and so on and so forth. So it's very dynamic. So it's easy to add and remove components, add and remove producers and consumers. It might have some problems in terms of scalability. Well, the event dispatcher might become a bottleneck. We will talk about quantitative analysis next time, but intuitively, if everything has to go through the event dispatcher, that might become a bottleneck. So, for example, for big systems, but I mean, you might have distributed event dispatchers, so distribute also that part of the architecture. But if you don't distribute the event dispatcher, that itself might become a bottleneck when you start having many producers or many events incoming, and of course many events to be relayed. And the other problem is that in event-based systems, it's the ordering of the reception of the events is not guaranteed. So you could have, imagine that, for example, C3 sends an event before C5 sends an event. It is not guaranteed that the receivers will receive first the event published by C3 and then the event published by C5. So you could have out of order reception of events. So if ordering is important, what you typically have to do, for example, is include some sort of, I don't know, maybe timestamp or information that allows you to reorder the events. But again, the ordering is still not guaranteed. So you might have to program accordingly in case the ordering is important. Some of the nice things of this architecture are the fact, again, I've already mentioned the fact that consumers and producers are loosely coupled. Also notice that the architecture is based on an asynchronous paradigm. Asynchronous because whereas, for example, in the client-server architecture, when the client invokes when the client invokes request a service on the server, of course the client waits for the response. So it's a synchronous mechanism. So you send a request and you wait for the response. In this case, this is a classic asynchronous mechanism where you send an event and then you don't wait for the clients, for the receivers to receive it. Actually, the event producer doesn't have any information about when the event is received. So there's an asynchronous mechanism. It is also a paradigm which is typically reactive. Reactive because, again, you are waiting essentially for events. So the consumers, they wait for events and then they react on the events. So the events typically act as triggers to maybe computations or maybe other events, and so on and so forth. As I've already mentioned, the producer doesn't know anything about the receiver. So who receives the message, who receives the event, is not actually is not determined by the producer. So there's a notion of so the location, the identity of the receiver is actually abstracted away. The producer doesn't know anything about that. It's the receiver who decides, okay, I want to get the data, and then again, as I said, we have the classic loose coupling between producers and consumers. So you can have, for example, one sender, multiple receivers, multiple senders, one receiver, though it's quite uncommon to have multiple producers and only one consumer. Still, it's possible. So you can have many multiple producers, multiple consumers, and so on. So it's a very flexible architecture that lends itself to a lot of modern applications. Okay, so this is for the event-based architecture, event-based style. Another style that's quite, I mean, again, came in vogue some 10-15 years ago. In a sense, we are following a chronological order in the way we are presenting the various styles. So the layer style, I would say, was the first one, then client-server, classic one, then event-based from the 80s and 90s, and the service-oriented is more like the year 2000, 90s, year 2000, and so on. So we are sort of following a chronological order in the way we are presenting these styles. So if you want, the service-oriented architecture is essentially an evolution. Well, let me say that it's an evolution of the client-server, but more sophisticated. More sophisticated because in this case, the idea is to, again, we have a decoupling between the server's requesters, so the components that ask for services, and the service providers. So in the client-server architecture, we have a very tight coupling between the service requesters who send the request and the service providers who answer. And essentially, the idea is that in the client-server architecture, as I said, the identity of the server is well-defined and typically known by the client at deployment time. However, the idea of a service-oriented architecture is to decouple, actually, the client and the servers a bit. Not so much as in the event-based. Again, in the event-based, who sends doesn't know who receives. In this case, who sends knows who receives, but the idea is that that is determined during runtime. So not at deployment time. So you discover essentially services during the runtime. So we still have, let me say a client side, so the requesters. We have a server side, the service providers, but we also have an intermediate layer of, as they are called in the slide, intermediaries, who allow, for example, clients to discover servers, so who provides services, the intermediaries, they also allow, for example, to keep a register of all the services that allows, for example, to discover, it allows you to discover who provides certain services, and so on and so forth, and also information, service descriptors, so the types of services that are offered, and so on and so forth. So, in addition to, the idea is that in a service rendered architecture, the end result is that the requester side is ultimately able to send the request to the provider side. But to do that, first, there are intermediate steps that concern, for example, the publishing of the service. So you have to notify the registry, essentially, that a service is available. There's a phase of service discovery where the requester looks for services and say, okay, who is able to provide the service? And then, after determining what is the service, what is the server that is able to provide me the desired service, there's the so-called service binding phase, where the requester actually binds to the provider and says, okay, now I know who can answer my request, and I'm going to send a request to that service. So there's this intermediate part. So ultimately, there's a requester side that sends a request to a server side that answers, but there's an increased dynamism with respect to the client-server architecture because, for example, even the shape of the request is determined or can be determined at runtime. Not only, it is not statically determined as it typically happens in the client-server architecture. So the idea goes something like this. So we have the requester side, that's the orange side. We have the provider side, that's the yellow side. And then there's the intermediate services, the blue side, the registry, that allows, for example, the service providers. So service providers, they offer services, and each service is described through a service description. So the idea is that the service providers, they actually publish the service description on the service registry, so that the service requester can then browse, can then discover, can then find the services by invoking the service registry, and then the service registry, for example, tells the requester, okay, this is a possible list of services that can satisfy your request, and then the service requester binds to the service provider for essentially exchanging information. So service rendered. So this is again if I remember well, there's an entire course on service-oriented development. Service-oriented programming and so on. So I'm not going to give any more details than this, but just to highlight another potential style. And then again, following this incremental, not incremental, chronological order. So following this chronological order, we move a more recent approach the last few years. This is a fairly popular buzzword right now. Microservices. So we move from services to microservices. So the idea is that in services, service-oriented architecture, services are big things. They offer lots of services, big descriptions, and so on. They manage a lot of data, and so on and so forth. The idea of microservices is to essentially parcel the architecture into small services that typically handle each small service handles its own data. So it's a lighter weight approach to a service-based mechanism. Lighter weight because if the services are small ones, so if they are let me say they are very much focused on their own data, on specific services, then it's easier, for example, to bring up new services or maybe shut down services. So it's a more dynamic approach where services can be more easily, let me say, put online, then removed, and so on and so on and so forth. So essentially, it's a way to again break down. It's a way to break down the architecture into smaller parts, which can be again brought up, brought down more easily. And by the way, just to give you an idea, for example, I do remember this from last year. The project. I remember there was a group who was very much enthusiastic about microservices, and they built their own project. Again, a good project, I have to say, if I remember well. They built their entire project on the idea of microservices. So they explored the microservices pros and cons and so on. And if I remember well, they did a good job of essentially, let me say, bringing a case or stating a case why microservices were a good approach for that specific application. So again, I'm not saying that everyone should do microservices in the application. You might consider them for your application. But again, it's a possible style. So I'm giving you a range of styles, a range of options. You might use one or even more than one of them in your application, where especially when you do the design part, essentially next month. Okay, so these are some of the styles. And then again, moving to modern problems. Let's have a look at some possible patterns for creating architectures, in particular in the cloud world. So again, this is patterns. If you want, I mean, you've seen design patterns in Ingegneria Software 1. For those of you who took the class here in Milan. So, or even if you took some basic concepts of software engineering somewhere else, maybe you have seen the idea of design patterns, model view controller, and the observer pattern, and whatever. So those are patterns for building, let me say, let me say, classic style applications. Yeah, of course, you can have the notion of pattern. It's a general one. So you can apply, for example, to architectures for example, for the cloud world. So let's have a look at a couple of possible patterns that you can use when architecting cloud-based applications. All these things, all that I'm going to show you is taken from this website, www.cloudcomputingpatterns.org. So if you want further details, you can look on you can go to the website and check the various patterns. So again, the website it presents a long list of patterns. Of course, it's not my interest to present you each specific pattern. Again, this is not a course on architecting cloud-based applications. It's just I just wanted to show you how to answer possible different needs. Let me highlight possible different non-functional needs, like responsiveness, like reliability, like, for example, the availability, the ability to handle increased loads. So to handle typically non-functional qualities of your application, you can think of different approaches which fit better. How can I say? Which can maybe help you solve some problems, maybe not others, and so on and so forth. So the question is, when you are trying to build an application that is responsive, essentially, supposing that the functional part is taken care of, so let me say the data, the computations are correct. When you are architecting your component, you are typically architecting it in a way that the load is spread around components in the right way, that the information is in the right places, you know where to access it, and so on and so forth. So you have to define patterns. You have to define certain approaches that allow you to meet these quality, let me call them quality requirements. So let's have a look at a few of these again possible patterns. In particular, we are going to have a look at the so-called stateless component pattern, the elastic component pattern, and the elastic load balancer pattern. So these patterns essentially are some of the basic ones. I would say even some of the more popular ones. For example, handling different loads of requests, and maybe also for example, mitigating problems like components going down, and so on and so forth. Let's start with the stateless component. So the idea of stateless components. So stateless components. As the name suggests, they have no state. What is the advantage of having a component that has no state? The advantage is that if the component goes down, so you essentially, for some reason, it shuts down, maybe the server has a problem, so it shuts down and everything. So if a component goes down, to bring it back up, you do not need to rebuild a complex state, because the component is stateless. So it doesn't have a state. It only provides functions. So the component goes down. To bring it up, you just bring it up again. But because you don't have a complex state to maintain or to recreate. Of course, the state must be the data must be somewhere. Essentially, a stateless component means that it doesn't really have data. So the data must be somewhere. Typically, data is on a different component that then could become a bottleneck, but that maybe, and maybe on the component with the data, you can focus on that to maybe make it resilient, to make it reliable, and so on and so forth. But the function, the component that computes the information, so that is stateless, so it's easy to create a new one, add a new one. For example, if you have to answer, if you have to reply to many more requests. So you have, if you have an increased number of requests incoming, and you have a stateless component, you can simply bring up a new component to handle the new request. Indeed, the stateless component pattern is also the basis for the other ones that we are going to see. Later on. So essentially, so this is the basic idea. The idea is that so the data, there's a storage component, there's a storage part which again needs to be made scalable and also reliable and so on, because essentially we are moving the scalability problem from the components that compute the functions to the component that manages the storage. But again, maybe it's one, since we are not focusing on the functions here, but on the data, maybe it's easier maybe it's easier to architect and to develop a component that only does the storage in a reliable, scalable manner. For example, you could distribute the data across different data stores to make it again more reliable, to make it faster. But essentially, the stateless components, which are these ones, they do not carry any state, so the data is persisted here, so you can bring them up and down essentially as much as you want. You can create a new one, remove an old one, if you go, for example, or maybe create a new one if a previous one goes down, and so on and so forth. So this is the basic pattern. So the stateless component. The second pattern is the elastic infrastructure. So in this case, so the stateless component is a single component, and by the way, as I mentioned, it's the basis for this second approach. So the idea of the elastic component is that we have an infrastructure that monitors the request, and depending on how many requests, for example, are received, when it sees an increase in a number of requests, then it, for example, provisions new servers, provisions new components that are able to handle the new requests. Essentially, the elastic component pattern, it's a way to automate the provisioning, so the monitoring of the requests and the provisioning of servers and of components, in particular, whenever, for example, the loads whenever the number of requests goes up, and so maybe that you have to answer multiple requests at a time, and so on and so forth. So again, the idea is that now we have so typically stateless components. For example, here. So these could be stateless components. So based on the pattern we have just seen, but they are part of a larger infrastructure, of a, let me say, more complicated infrastructure, where we have a further component which monitors the requests. So we have a scaling manager that analyzes what's going on in the system, and that is able to automatically provision, to create new components, or maybe remove components when they are not necessary. So by essentially invoking a suitable API. So there are APIs. So in this case, the keyword is automation. The keyword is that we automatically create new components or remove old ones when they are not needed, or when new components are needed, and so on and so forth. So this is the elastic component pattern. A further evolution is the elastic load balancer. So in this case, the elastic load balancer is focused on, for example, distributing the load across components. So again, it's an evolution of the elastic component pattern that we just saw. So in this case, the idea is that the elastic load balancer actually it's a gateway to the request. So in this case, you see in this picture. So the elastic load balancer it actually not filters, but looks at the requests that go through it, and depending on the request and depending on the monitoring of the infrastructure, so it sends the request to the right components. But when it sees that maybe the components are not enough, it can use an API similar to the one that we just mentioned for the elastic component. It can use that API to provision new components, which are again typically stateless components. So provision new components so that then it can relay the request to those components. So essentially, the elastic load balancer is built on the idea of the elastic component. The difference is that essentially that component is really the one that monitors and sends and relays the request to the various components, and it also decides, for example, whether to provision new components or not. Again, the idea is that the balancing is done automatically. So the keyword here, as in the elastic component, is automation. Automation of the provisioning of the components, of the removal of the components, and so on and so forth. Okay, so again, if you're interested in further details on these patterns, but also on other patterns, because maybe you have to program or develop your own cloud-based application, you have the link to the website in the first slide. Okay, so then the last part for today. So again, these are just very quickly a few styles, possible approaches that you can use when you architect your application. For example, again, the application for your monitoring project. So as I said, instead of doing this on Friday, we're going to do it today. I want to show you a couple of examples of real-life systems that, as case studies, for what a good architecture can do for you. So essentially, in both case studies, and the two case studies are a popular web server, Nginx, and a popular structure for a compiler, which is the LLVM structure. So both, of course, are very important pieces of software. Web browsers, not web browsers, sorry, web servers. Web servers are, of course, a very important part of the computing infrastructure these days, and then, of course, also compilers. I mean, of course, when you're programming, most of the time you are compiling. So it's important, for example, that compilation is done efficiently, and so on and so forth. Now, so I'm going to focus on Nginx and LLVM. In both cases, the two solutions, so Nginx and LLVM, came about as, let me say, answers to shortcomings in previous architectures. So in the case of Nginx, Nginx has been around for some 15 years. The most popular web server was, at the time, and still is actually, I saw some data yesterday, said like some 40% of servers still run it, is Apache. So the Apache web server from the 90s, it was the most popular architecture, the most popular solution when Nginx came to life. And Nginx is actually an innovative architecture with respect to Apache to answer some of the shortcomings of the Apache architecture. Shortcomings, again, not from the point of view of functions offered. The functions offered by the Apache web server were perfectly fine. The problem was performance. The Apache web servers, when Nginx was developed, was not able to handle too many requests at the same time. So there was a need for a better architecture for the web server to actually handle the increased amount of requests. So you see, the problem was not a functional one. The problem was not that the outputs were incorrect. The problem was a performance one. And how to answer a performance problem, you do that. You can improve your algorithms. But one way of answering your performance constraints is to devise a better architecture. So again, notice how architecture is created to help answer quality requirements like performance, reliability, availability, timeliness, and so on and so forth. Similarly, again, I'm going to give you a bit of an overview of the two approaches. Similarly, the LLVM approach, which was essentially an answer to the classic GCC compiler suite. So GCC is still, I would say, the most popular approach used in practice, but it also had a number of shortcomings, in this case not so much in terms of performance, but in terms of extensibility, in terms of adding new features, in terms of adding new optimizations, and so on. So, for example, it had a number of shortcomings from the point of view of the modifiability of the architecture. Again, not from the functional point of view. GCC was doing fine. I mean, it was actually producing a binary code fine. That was not the problem. The problem was that when people wanted to extend the compiler, it was difficult to do so because it required extensive modifications to the whole compiler. So what people did, again, some 15 years ago, they developed a new architecture that made it easier to actually create new modules, add new optimizations, and so on. So again, the improved architecture was not an answer to a functional issue. It was an answer to a quality issue. A quality, in this case, a quality problem in the development of applications that were difficult to develop. So these are two interesting. Case studies. Okay, so also, I mean, they can also serve. They can also serve as, again, possible ideas. I don't know if the things presented in these two case studies will be useful for you in the monitoring project. But again, looking at different possible solutions, different cases, can help also identifying your own ones and maybe realize how things can be done better, maybe also in your code. So let's start with the first one. So Nginx. A bit of history, which is you were not born yet, I think. Most of you, I would say, are from the 90s. I mean, most of you were born in the 90s, I imagine. 92, 93, and so on, 94. So this is what I'm talking about here is exactly from those years. I remember that actually. I was a user. I was a user of this. Actually, I was a user of the previous version of this. Which is consigned to the, I guess, history books. The first web browser, actually, so the first browser were like command line. I tried using them. They were really painful. Then in the 1993, 1994, if I remember well, it was like a big evolution. The first graphical web browser was created. Was called Mosaic. I don't think it exists anymore. I don't even know if you ever heard of that. So Mosaic was a big breakthrough. You could browse graphically. You could type in the URL and see the page. It was a very eventful change. But Mosaic was still confined to essentially universities. I was able to work on that because I was at university at the time, and my university actually I wasn't here in Milan. I was abroad. We had servers and we could browse using Mosaic. But then after a few years, well, 95, 96, so Netscape Navigator came about, and that was actually also a further improvement. For a few years, Netscape Navigator was definitely the most popular one. Then Microsoft Explorer came around. I don't even know if you remember that, but there were lawsuits. Essentially, Netscape Navigator was the most popular browser for a few years until Microsoft started essentially shipping computers with a pre-installed Explorer. So then Explorer became the most popular, and actually there were lawsuits which Microsoft lost, and so on. But this is a bit of history. This is a bit of history of browsers. Just to let you know, this is just to mention that in the second part of the 90s, so 95, 96, 97, when browsers became easier to use, again, early 90s, command line, it was just painful. Then they started becoming graphical, and Netscape Navigator was quite efficient for the time, for the things of the time. So essentially, that led to an increase in traffic. So, at this time, first of all, the internet was a very different thing than it is today. I would say very little multimedia. Pictures, you could see pictures, but videos and that kind of stuff, it was not the case. So there was not a lot of intercommunication going on, and also they were quite static. Like you could, for example, I don't know, get some display a page, but getting, for example, transactions where you have multiple interactions with the same web page, it was not the case. It was not what happened at the time. However, so in this case, essentially, also communication was very, very slow. I don't know if you've heard. I don't know if you've seen actually the old modems like 56K kilobytes. Those that when you started going and so on, they made a very strange noise. That's prehistory. That's 20 years ago. It was very, very slow. So it was really a pain in the ass working with those things. Still, since data transfer was very slow, there was no need for very efficient, for example, architectures. So the web server, so they developed the Apache web server came around at that time. And there was not a big need for example, handling a lot of data simultaneously and so on and so forth. So the architecture was driven by that quality concern in the sense, or maybe not driven by the quality concern. There was not really a need to, for example, be able to handle a lot of requests at the same time. So they went for a structure that favored, let me say, simplicity of programming over efficiency. And in that case, the architectural solution that they chose was to essentially, again, came from the classic Unix approach of processing and spawning processing. So the idea is that each request is a new process. So you don't have many requests incoming. So again, for the 90s it was enough. So you don't have many requests incoming. Every new request spawns a new process. So you are more easily able to handle all the requests within the same process. It's more isolated, easier to program, and so on and so forth. So again, this is the. I don't want to enter all the details. I just want to point out the fact that whenever a new request was incoming, what the server was doing, it was a fork. It was forking a new process to handle the request. So every new request is a new process. So it was also a very well-known programming style. I mean, that had been around 20, 30 years. So people knew it very well. So it was fairly easy to program. So they went for that solution. The problem is that every time you spawn a new process, it takes with it a lot of memory, all the memory. So it copies all the memory, everything of the parent process. So you end up consuming a lot of memory for each process, even if the process didn't need to do a lot of stuff. Even though the process was doing very simple things, maybe, I don't know, displaying a page, it consuming as much data, if you want, as the parent. So it was quite memory consuming. So the problem is that so it was fine in the 90s essentially. So again, when connections were not that many, the data transfer was not that much. It was fine for some time. But then again, networks improved. We started having DSL. Actually, the first optic fibers in Milan are the end of the 90s, early 2000. That's when, for example, in Milan, we started getting some 10 megabits per second, which was quite an improvement with respect to the old speeds. So traffic started increasing, and essentially, instead of having few, let me say, maybe even hundreds or thousands of requests, we started having to handle tens of thousands of connections at the same time. So the old architecture was not enough any longer. Just to give you an idea. Imagine that each process has some 2 megabytes. Some 2 megabytes of memory, static memory allocation, then maybe 1 megabyte of page memory, then maybe some between 10 and 100 megabytes for core memory. I mean, that's like 100. That could be a few tens of megabytes per process. So if you have a few tens of megabytes per process, and you end up having 1,000 processes, 1,000 clients, you end up having the gigabytes and gigabytes of RAM. By the way, 100 gigabytes of RAM might be available now. They were not available early 2000. So this went way over. This went way over the possibility of RAM at the time. So essentially, spawning a process with all its memory every time you got a request was not a viable solution. Was not a viable solution any longer. So people had, they devised a different approach. So different approach, Nginx. So Nginx is not so much request driven, much more event driven. So in this case, there is not a new component per request. Each component handles multiple requests, and it handles them in a lightweight manner. So essentially, each component waits for events, waits for, let me say, triggers. And these triggers could be, for example, the opening of a connection, the closing of a connection, or maybe the availability of the response from the server, and so on and so forth. So each component handles many of these events, but these events, they are not handled per, let me say, requestor. So each component handles multiple requestors, so multiple incoming requests for opening a connection, multiple incoming requests for maybe closing a connection, and so on and so forth. And the number of components that handle events is fixed. It's fixed, and typically it's equal to the number of cores that you have available. So whereas in the classic Apache structure, the number of processes is independent of the number of cores. You typically have many more processes than the number of cores available. You could have 10,000 processes and only have at the time 1 or 2 or maybe 4 cores available. In this case, the idea is that each component, you have a component handling events per core, essentially. So each core handles different requests. And And the idea is that the structure, the framework is programmed by using non-blocking operations as much as possible, so that concurrent threads, so concurrent requests, do not essentially interfere with one another. So this is taken from the web. I mean, this is, I think, from the Nginx website. So you see, the idea is that you have a number of workers, typically one worker per core. Each worker handles incoming requests, opening the request, closing the request, and it actually interacts with the backend, which answers things at its own pace. So the idea is that the worker, for example, takes the request, relays it to the server side. The server side processes it. When it gets a response, it sends it back to the worker, which sends it back to the client. But the client, or actually the worker, is not blocked while waiting for the response. So it's an event-based architecture. So the event response is ready is what, let me say, wakes up the worker so that it can then relay the answer to the client side. So a worker in this way can handle multiple requests at the same time, waits for the completion of the solution. When the solution waits in the sense that while the solution is computed, the worker does other things. When the solution is computed, then it gets the solution and sends it back to the client. So you notice that it's an asynchronous mechanism. Asynchronous. You are not waiting for the answer. The client is waiting. This client side is waiting, but not the worker. The worker is not blocked waiting for the answer. It simply goes on, handles other requests. When the answer is ready, it takes it and sends it back to the client. So it's an inherently asynchronous approach, and it's a non-blocking. It's a non-blocking one. So essentially, that increases the level of parallelism between the various components. So essentially, it allows you to handle many more requests than it was previously available. And as I said, typically you have one worker, so you have as many workers as you have CPUs in the system. So typically, however, so this is let me say, the good part, the advantages. The advantages of the approach, where you are able to handle many requests at the same time. So essentially the same worker handles many requests at the same time, because it gets a request, asks for the solution. In the meantime, while the solution is computed, it handles another request. So it's handling, for example, multiple requests while the solution is computed, and then the solution is computed, and then it answers. The problem with this is that programming this kind of mechanism is more difficult. With respect to, for example, the classic sequential programming that was done in the classic Apache structure. So when you have a separate process per request, it's a sequential programming, because again, everything is isolated. So you program your process that does 1, 2, 3, 4, 5. You don't need to interleave. For example, while I'm computing this, I also need to handle an incoming request. While I look for stuff on the hard drive, I also need to handle another request. So if you have a process-based mechanism, essentially each process does its things sequentially, 1, 2, 3, 4, 5, and has its own memory. So it doesn't need to coordinate for memory access with other processes. Instead, in this more dynamic, more parallel architecture, workers, they need to share memory. Because in this case, you don't want to have a separate memory space per worker. So essentially, this makes things more complicated because then we need to handle synchronization of the data. So that's why the emphasis is on using non-blocking operations. So you don't want to block, for example, access to memory while you're doing stuff, so that maybe other people are not able to process their request. So essentially, whenever you make a modification to the memory, to some part of the shared memory, then you need to notify all the workers that some modifications have been made, so that you know that maybe you need to, for example, reload the information from the memory, and so on and so forth. So it's more complicated because you need to coordinate the various workers sharing the memory. So it's very so the advantages is the increased parallelism, the increased ability of answer, the increased ability of handling requests. It's more conservative from the point of view of the memory because, again, the memory is shared. So you don't need new memory every time you have a new process. In the Apache structure, every time you have new request, new memory must be occupied. In this approach, you have shared memory, and to handle a new request, you might need maybe a little bit of more memory, but not much. Essentially, the memory is associated with each worker and doesn't change much. So it's really it's much more conservative from the point of view of the memory consumed. And then, as I said, essentially one worker per CPU, one worker per core. So it's really you're using each core at its maximum possibilities. The problem, so the disadvantages are essentially on the programming side. They are more difficult to program, to synchronize, and so on and so forth. It's again less intuitive to program, even though it's more efficient. So I've already actually mentioned the advantages of the architecture of the Nginx solution with respect to the Apache solution. Just let me mention that so actually Apache, the slide hasn't been changed for the past few years, but it's still true. Apache is also, it says there, partly transitioning to an event-driven architecture. Apache now has different actually solutions to handling requests. The classic one, but also a more event-driven one, which has recently become stable. I checked actually. So again, it's not, Apache was not natively event-driven. So when they had to move the framework to an event-driven paradigm, at least partially, they had to rework a lot of the framework. Instead, the Nginx architecture hasn't really changed for the past 14 years. It was good. It was good at the time. It was able to handle 14 or maybe even more now. It was good at the time. It's still good. And so they didn't really need to overhaul the architecture to handle maybe increased requests. So that is the mark of a good architecture. It's able to change. It's able to not evolve, but it's able to essentially adapt and sustain, for example, increased loads, even if maybe at the beginning they were not foreseen. So Apache has been reworked, but still, as I said, it's not really. Apache was not conceived from the beginning using an event-driven approach. So they are adapting it, but with some difficulties. Only recently, apparently, it has become stable. So that is the first case study. The second case study, as I said, this is in the compiler realm. This is in the compiler domain. And in this case, it's the so-called LLVM approach. Now, I never remember, but again, I checked. LLVM originally stood for low-level virtual machine. Originally, LLVM was an acronym for low-level virtual machine. It was started some 15 years ago, and then it evolved to a general approach. So now LLVM stands for LLVM. So it doesn't really correspond to the old acronym any longer. So it's just LLVM. So it happens that things that initially have a meaning, they essentially do not really change purpose, but they evolve. So in the end, the acronym becomes the name. So LLVM is now the name of the architecture. And the LLVM approach came about as, again, a response to shortcomings in the way compilers were built. Now, ideally, a compiler has a very, let me say, linear structure, because a compiler takes as input some source code and must produce some machine code, some binary code. How does it do it? It typically has a front end, and the front end is in charge of reading the source code, building the syntax tree. So the front end essentially reads the source code and creates internal data structures for essentially navigating the code. The back end is in charge of generating the actual machine code, and in between there are some optimization functions that maybe allow you to remove unnecessary code, optimize some code, optimize memory consumption, and so on and so forth. So in principle, the structure of a compiler is very simple. You have the front end that takes as input the source code. The front end creates data for the optimizer. The optimizer optimizes the information, and then it sends data to the backend, and the backend produces the machine code. Very linear structure. That works if you are handling a single programming language. So for a single programming language, that's fairly let me say, well-defined, easy, let me say, no big deal. The problem is, what happens if you want to have, if you want a single compiler for a single programming language, but a compiler infrastructure that is actually able to handle several programming languages and then produce, for example, binary code for several platforms. So what happens if, instead of having one possible type of source code and one possible type of machine code, you have several possible input languages: C, Fortran, Ada, C++, Java, whatever, Python, whatever. And then you have several, possible outputs. So, for example, for x86 architectures, AMD64, ARM architectures, PowerPC if they're still around, etc., etc., etc. But in any case, so what happens if you want to have several languages and several machine codes? It could even be, imagine that you want to have something maybe a bit more modern, like possible input languages, Java, C#, and so on, and as output possible bytecode, for example. So maybe even different types of bytecodes. I don't know. So what if you want to decouple the machine code from the source code. So in this approach, the source code is very tightly coupled to the machine code. So one source code, one machine code. In this case, you could go C for ARM, you could go C for x86, you could do Fortran for PowerPC. So you want to be able to handle many more solutions. Of course, in the old structure, you would have to have one compiler, one compiler, one compiler, one compiler. So of course, it becomes essentially a nightmare to handle. So the LLVM architecture was developed as a response to this problem. We want to decouple the front-end side from the optimization side, from the back-end side. So, and the solution adopted by the LLVM will be, as I guess at this time we will see next time, to adopt an intermediate language to essentially separate these three layers. Okay, so I still need some 10 minutes, so I'm going to stop here. Tomorrow we are going to have the lab discussion on the monitoring project, and we will discuss also what you are supposed to provide, the standard, the IEEE standard for requirements for the document, and so on. And then if you have questions about the project, I can try to answer them tomorrow. And then on Friday we will finish briefly this part on the LLVM approach. Then we will discuss the flip classes, and then we will see the quantitative approach to analyzing architecture. So see you tomorrow.